So, a very good morning to everybody present here today. I am Srimanti Banerjee, a diploma level student at IIT Madras, and I'm also a third year student pursuing BTech in CSE. I'm here today to talk about the theory of congruences. So, I'll just share my screen now.
Yes,
So, is it visible?
yes.
So, this is a topic that has a great relevance in terms of computer science, cryptography, and so on. So, I'll just straight away start. Now, all of us have come across questions which are related to divisibility in our school days, right? Now, one approach to these is through the arithmetic of remainders, or what we commonly know as the theory of congruences, which is our topic of discussion today. The concept, along with the notation, was first introduced by the famous German mathematician Gauss. Now, let us take a look at what this is all about. Now, let n be a positive integers. So, two integers, a and b, are said to be congruent modulo n, which is symbolized by what you can see right here. This means that n divides a minus b, or when a is divided by n, we get a remainder of b. Now, moving over to some basic properties. The first property that we have over here says that A is congruent to A modern, which is pretty self-explanatory, right? Because this simply implies that A minus A is divisible by n, because A minus A is 0, so of course it is divisible by n. Now, taking a look at the second property, if A congruent to B mod n, then B congruent to A mod n. Now, I'll give a quick explanation for this one. So we know that if A congruent to B mod n, this implies that A minus B is equal to n into k, where k is some integer. So this also implies that B minus A is equal to n into minus k, which gives us B congruent to A mod n, right? So coming to the third property now, if A congruent to B mod n and B congruent to C mod n, then A congruent to C mod n. I'll give a quick explanation for this one as well. So the explanation goes like this. From whatever we have over here, we get a minus b equal to kn and b minus c equal to k dash n, right? Where k and k dash are integers. Now, if we add these two equations, we get a minus c equal to k plus k dash into n, which is basically a congruent to c mod n. Now, let us take a quick look at some more properties. So we have over here, let A congruent to B mod n and C congruent to D mod n. Then A plus C congruent to B plus D mod n. And the next property says that if A congruent to B mod n and C is some integer, then we have A plus C congruent to B plus C mod n, A minus C congruent to B minus C mod n, A into C congruent to B into C mod n, and A power C congruent to B power C mod n, where C is greater than equal to 1. Now here is a question which involves some basic properties. So the question goes like this. What is the remainder obtained when 2 power 50 is divided by 7? So what I do here is 2 cube congruent to 1 mod 7. This is what we know, because 2 cube is 8, right? So we have 8 congruent to 1 mod 7. Now we raise the power of both the sides by 16. So from here we get 2 power 48 congruent to 1 mod 7, right? Then we multiply both the sides by 2 squared to get 2 power 50 congruent to 4 mod 7. So I'll just discuss why I did the solution the way I did. Because see, it's always easier to raise the power of 1 or minus 1, right? Because we'll always get a result of 1 or minus 1. So I chose 2 power 3 because it gives me a 1 in my right hand side. And then I had to get to 2 power 50. So I raised it by 16, which is the closest that I can get. And then to get 2 power 50, I multiplied both sides by 2 squared. Hope it's clear. So here in the RHS, we get a remainder of 4. Now moving on, let's take a look at this question that prove that for any positive integer n, 11 power 12n plus 6 plus 1 is divisible by 13. Now for solving these, we do need some theorems, which I'm going to discuss very briefly. So first we have Fermat's little theorem, which is a very important theorem out here. So it says that let P be a prime, and suppose that P does not divide A, but A is an integer. Then we get A power P minus 1 congruent to 1 mod P. Moving over, we have another theorem, Wilson's theorem, which says that if P is a prime, then P minus 1 factorial is congruent to minus 1 mod P. And finally, we have Euler's theorem, which says that if n and a are coprime positive integers, and phi of n is Euler's torsion function. Let me just briefly say what phi of n is. So for those of you who don't know, phi of n basically gives us the number of numbers which are relatively prime to n. So the theorem states that if n and a are coprime positive integers, then a power phi of n is congruent to 1 mod n. Now, I haven't really gone into the details of the proof because of the time limit that's there, and also the previous basic properties that I explained, which I didn't discuss the proofs of. I have left those as exercises for you to try out later. They are very simple. They can be derived in a manner which is similar to what I discussed earlier for the last couple of properties. So now coming back to the previous problem. So by Fermat's theorem, we know that a power p minus 1 is congruent to 1 mod p. Now here p is 13 and a is 11. So we raise the power on both the sides by the basic properties by n, and we get 11 power 12n congruent to 1 mod 13, right? Now we need to get a plus 6 out here. So 11 power 6 equal to 11 square whole cubed, right? Which is 121 cubed. Again, 121 is congruent to 4 mod 13. So if we raise both the sides by a power of 3, we get 121 cube congruent to minus 1 mod 13 after evaluation. This is a pretty simple calculation. So from these equations, we just multiply and we get 11 power 12n plus 6 congruent to 1 into minus 1, that is basically minus 1 mod 13. And from here we get 11 power 12n plus 6 plus 1 congruent to 0 mod 13. So basically this shows that this term is divisible by 13 since it leaves a remainder of 0. Now I would like to go over to some divisibility rules. So all of us are familiar with the divisibility rules that we learned in our school days, right? So for numbers of the form 2 power n, we had to check the last n digits to see if the number is divisible by 2 power n. Like for example, for 2, we had to check the last digit. Is somebody saying something? Sorry, I'm unable to hear.
Yeah, yes, I'm getting something. Please mute yourself. Like whoever is not.
नहीं था वो हाँ यूनिवर्सिटी ऑफ मिशिगन वाला दूसरा वाला दूसरा का है फिर एक काफी है
Sir, should I be continuing?
No, just a minute.
Yes.
तुम जोड़ घटाव सीखना है तो तुम
And Srimati, you can
Yes.
unmute yourself and you can start presenting. Yeah.
Sir, am I audible?
Yes, yes.
Okay. Okay. So I'll just start from here once again. So what we did for, let's say, sorry. Okay, so what we did for 2 is we would check if the last digit is divisible by 2, right? Because we can express any number as x into 10 plus b, and 10 is already divisible by 2. So if the number altogether has to be divisible by 2, we just need to check if the last digit is divisible by 2. Similarly for 4, since 4 can divide 100, so we just need to check the last 2 digits, okay, which is denoted by c over here, and we can continue this for the rest of the numbers which are of the form of 2 power n. Now, yeah. So now if we come to the divisibility rule of 3 or 9, we know that if we check the digit sum of a number, if that is divisible by 3 or 9, then the original number is divisible by 3 or 9 respectively, right? So the reason behind it is very simple. Say we have a number of PQRS, okay, of the form PQRS. So when we expand it, we basically get P into 1000 plus Q into 100 plus R into 10 plus S, right? Now, please notice that 10 power n is congruent to 1 mod x, where I have just used x for denoting 3 or 9 since both the rules are the same. So now, say I'm considering this portion only. So I have P into 1000 congruent to P mod x. Why? Because 1000 is congruent to 1 mod x. I'm just multiplying P on both sides, right? And similarly for Q, I have 100 congruent to 1 mod x, as we saw over here. And I'm multiplying Q on both sides. Okay, I'm continuing this for each of P, Q, R, and S. And when I sum them up, when I sum these four up, on my left hand side, I get this equation right over here, which is basically my number, PQRS. And this is congruent to P plus Q plus R plus S mod X. That is the digit sum. P plus Q plus R plus S is basically the digit sum. So if this remainder is divisible by 3 or 9, it basically implies that the entire number is divisible by 3 or 9, right? So hope it's clear. And here are some problems for you to try out later. So I would first like to say the second problem. As I discussed the rules for 3 and 9, you can similarly figure out the rules for 11 and 13. So what should be the divisibility rules of 11 and 13? This is a problem for you to try out later. And we do know that there are infinite number of primes, right? There are a lot many proofs for it. So I want those who are interested, they can prove that there are infinite number of primes of the form 4k plus 3, which is also another way of saying that there are infinite number of primes. So that's all for today. Thank you.